Welcome to the 5th webinar in Qualmark's 6-part Ask the Expert series titled Achieving Warranty Cost Reduction Goals with Effective HALT and HASS. This series has been developed to provide a comprehensive overview of setting up and running an effective accelerated stress test program that will deliver tangible results in support of warranty cost reduction programs. I am Gail Eckert, Director of Marketing for Qualmark. I'll be your moderator for today. Tom Peters, Qualmark Center of Excellence Director, is hosting this special series designed to provide key information for performing effective HALT and HASS so that customer accelerated reliability programs can provide maximum impact for meeting business goals. Session 5 follows up on last month's presentation, which demonstrated effective HASS on a medical device. Today, Neil Dortenbaugh, Qualmark's Senior Application Engineer, will provide an overview on effective HASS screening. Tom, as host, will you get us underway?
Thank you, Gail, and thank you everyone for joining us this morning. As Gail mentioned, this is the 5th in the series of 6 modules, and as you're noting, these are being recorded so that if you have missed any of the previous modules, you are more than welcome to log on to the Qualmark website and you can review the recorded modules. Just a short history of what we've gone through. The first module, we talked about setting up a HALT lab, an effective way to set it up so you get optimum results. Part 2 was part of the liquid nitrogen infrastructure, which is very key to getting good performance from your systems. And then in Part 3, we explored actually conducting HALT on a power conversion device for computers, and that was done by Dave Ray, and we talked about how HALT is used in the IPC 9592A standard. Following that, the last month's module was effective HASS on a medical device, where John Hansen of Varian Medical talked about their experience setting up HALT and HASS in their system and the wonderful results they were able to obtain using HALT and HASS and the Qualmark Q Fusion. And today's presentation, Neil will go over and talk about essentially moving from HALT to HASS and creating an effective HASS screen. Neil, you want to go ahead and take over from here?
Thanks a lot, Tom. Last month's presentation covered a specific example of HASS. What I'd like to get into today is, in general, the process of implementing a HASS screen, the key elements that you need to concern yourself with, and some of the pitfalls to avoid, and how Qualmark can help you along the way. In general, we'll be covering what HASS is, how we describe it, and then going on through the whole process of the goals of HASS and how to set up the screen. I always like to begin with a basic description of what we're talking about. There are a lot of different ways that people define acronyms like HALT and HASS and how they use them. When we're talking about here, HASS, the highly accelerated stress screen, is a production screen. 100% of the product is tested. It uses the vibration and thermal stresses that are the same that are used in HALT or similar type. And we base the limits of the screen on what is found in HALT. And this is a key part of HASS as the way we define it. Limits are found based on HALT. Now, the goal of HASS, in general, in a simplistic term, is to continuously verify that the limits you found in HALT haven't been compromised. You have used HALT to find out what your limits are and to push them out as far as you possibly can. With HASS, you're testing to approach those limits and see if there's anything new that has crept in. Anything new, any new weakness tends to be something that will come out very quickly at lower fatigue levels. So we can use safe lower fatigue levels in HASS and force these weaknesses to become detectable so that we can get them out of the line and keep them from shipping. Another key thing that happens both in HALT and in HASS is not only are we fatiguing and forcing things to break, we're also forcing malfunctions if some component has shifted its characteristics, perhaps not sufficiently to make a system shut down or cause a hard failure, but enough to change a key performance indicator that will give you a hint that something has happened at a vendor that has shifted a distribution that may result in problems in the field. These are all the key goals of HASS. All of those goals very directly impact warranty costs. We'll be detecting and correcting any changes that will that are unintended or were intended but not intended to reduce reliability. You will reduce production time and cost with a HASS screen because if you compare it to a typical burn-in, it happens much faster and you can get it done with less expense. And you'll find things you can't find any other way, which is why you will increase your out-of-box quality and your field reliability. I'll show you some graphs that describe that in a little bit more detail later. But getting a new product released without having it stumbling as it goes out the door, but instead having those first ones that are going out being just as reliable as the ones that you're producing at the end of the year is an important part of what HASS gives you. And it gives your servicemen a break so that you have fewer service issues because the units that ship last longer. Now, I had mentioned that the levels that you use in HASS are based on what you found in HALT. And HALT, as most of you know, is the test that's done in design to push the limits as far out as you can in your design. When you are doing HALT and you know that you will be doing HASS and you know that what you find in this HALT is going to determine the limits that you use in HASS, there are some special items to consider that we'll cover that are important to get the basis that you need to implement your screen well. One of the first things to consider is that the failure analysis and corrective action that we always emphasize as part of having HALT done is particularly important when you know you're going to be getting into HASS. If you leave items, find something in HALT and you unwittingly allow a reluctant engineer to say, you know, it happened so far out of spec, I really think we don't need to worry about that one. It will pop up in HASS as the edge of a distribution and will be something that gives you trouble as you try to get your screen implemented. Look very carefully at the failure analysis and corrective action. Make sure that everything's been well addressed. And that fact does highlight that with HALT, we try to impress the importance of making a good report, keeping good records, making sure you know exactly what stresses caused what failures. When you know you're testing and getting ready for HASS, that's particularly important. Now, one of the things that we discuss and comes up occasionally when we talk about doing a HALT is if I know I'm going to be going into HASS, isn't it going to make a difference that when I HASS, I typically use a different fixture assembly and sometimes fixture at a different assembly level than when I'm going into a HASS. In HALT, as you can see in the left-hand picture here, it's not unusual to take devices apart, fixture boards out independently so that we get better vibration and better thermal change rates on the unit. But when you get into HASS, you're going to be typically testing full-up units. Sometimes it may make sense to do your HASS at a subassembly level. That's a decision that needs to be made. but often it's a full-up unit that gets tested. So the question is, if I'm going to do halt knowing I'm going to do HASS, should I be doing it like this with my units disassembled? In general, the answer is you want to do the very best halt that you possibly can. Make sure that you're doing halt as effectively to get the best results you can. Don't worry about differences, especially differences in product orientation between halt and HASS. The halt orientation, for example, if you want to lay a product down or stand it up, use the best orientation that makes sense for halt to get the best energy into it. And if you have to change that orientation when you move into HASS, then you make the correlations when you get into the HASS fixture and make a decision based on what you find out. And it's not unusual to have to go through that process. If a product is much taller than it is wide, then you'll often lay it down when you do a halt so that the fixturing is more effective. But then when it comes time to do HASS and you want to put as many as you possibly can into the chamber, then it comes time to stand that product up. And that change in orientation will have a change in the excitation that you see, but you don't want to try to mimic that necessarily in halt. Do the best halt you can. You'll note that the product that's shown here is being fixtured centered on a quadrant. That's typical in halt and in HASS to realize that the vibration is uniform across the table in quadrants. As you're centered in each quadrant, you'll see approximately the same vibration. Whenever we do fixtures in halt, for HASS, when Qualmark designs HASS fixtures, we design them based on that. And when you do halt, you should center in the quadrant as well, just to reduce the number of variables that you have to deal with. So keep in mind, as you're doing that halt, documentation, data considerations, you've got to keep good track of everything. That way you can do accurate comparisons of product response in different fixtures. Make sure that you have very carefully recorded the locations of transducers, because a slight change in the placement of an accelerometer can give you a very different reading. When I'm checking to see how much difference it's really made to rotate my product 90 degrees, making sure I have the accelerometer in the right place will make a big difference. So take lots of pictures and use as many accelerometers and thermocouples as you can. Also, make careful record of any customizations that you did in halt. It's not unusual to start drilling holes in cases in halt, but they do tend to frown on that in production. So you need to understand those differences as well. They're very important. Now, once you have completed that halt and you have the basics that you need to get HASS started, you have to start thinking about the fixturing for HASS. Fixturing in HASS is much different than fixturing in halt. Fixturing halt tends to be pretty straightforward, and you can be as creative as you like because you only have to make one of them. With HASS fixtures, you are expected to create a fixture that will provide a qualified screen that is reliable. You have to realize that a fixture takes a lot of abuse in HASS, and you need a fixture that can stand up to it. So it needs to be reliable and durable, and also able to get product in and out quickly and easily. It is in production. It needs to be able to tolerate all the temperature extremes the chamber can provide, and do all that without damaging the product itself. And now we're looking for things like cosmetic damage even, and that can be, when you consider the vibration and thermal extremes the chamber is capable of, making sure that the product comes out of it without cosmetic damage is a key challenge in designing fixturing. The basic things you want to keep in mind, well, oddly enough, we want to be sure we're getting vibration transmitted well to the product, just as in halt, but it can be a little more difficult now because we don't have the luxury of allowing metal contact directly to the product. That might give us the cosmetic damage we don't want to see. And make sure we're getting adequate thermal excitation. When you don't have a chamber very full, like you typically are in halt, then thermal airflow is pretty straightforward. You don't have to worry about it much. When you have a chamber filled as full as you can get it with product, which is often the case in HASS, now you have airflow considerations to look at. And that may mean some custom ducting or some changes in the position of the product to allow good airflow and adequate change. You also have to consider in your HASS design that you're providing for all your cables and connections. There's a big challenge of getting all those in and out and made so that you can connect them easily. So providing for all those is another challenge in HASS, in the HASS fixture design. As I said, making sure you don't damage the product and meeting those human factor concerns. You got to watch the sharp edges and make sure that it's easy to reach into and load. There we go. Here you see several products. In this case, we're looking at power supplies that go into servers. And this is a single fixture. And what you see here are these fixtures loaded into. This is our Q Fusion product, our latest product designed for use specifically in HASS in high volume environments. So you see we have 6 independent tables, each one with the same fixture on it. And in this case, we have pneumatic actuators here that are driving this nylon or Delrin clamp down onto the product. And each of those pneumatic actuators has the pressure independently controlled. As part of the validation of the fixture, we determine the levels to use there to assure that we're seeing equivalent vibration across the fixture. Once that's done, we simply duplicate that for all the fixtures in the system and fixture multiple product that way. If you have larger product and are looking at doing HASS in one of our standard systems, here's a HASS fixture of something fixtured into, as I had recommended, a single quadrant. And here we have 4, looks like larger power supplies being mounted in. You can see bolted down to the table here. So it gives you an idea of the range of products that will go in. Here's a picture that's interesting simply because we've got so many cards going into motherboards that are in the back of the fixture here. Also, you'll note that the fixture is being populated outside of the chamber. This fixture is designed to be fully populated and turned on, checked out outside of the chamber, and then put into the chamber so that you can do the loading and unloading process much more quickly. And this fixture design actually emulates the configuration of the product in its final use. It's mounted into a system that has a double row of backplanes here, and here you see a power supply and all the interface cards that are necessary are back in this area of the fixture. But each one of those pieces, which as you can kind of tell from the size, is designed to fit in a quadrant, is loaded outside and then dropped into the chamber from there. So here's some of the things to keep in mind when you're looking at the design of a HASS fixture. Number one is to minimize the use of tools to fixture the product. It's difficult to get inside of a chamber and use tools when you need to do it quickly and you're reaching into the middle of the table because typically you have the whole table full of product, trying to make the best use you can of the table. It takes time and it can be inherently difficult to repeat things like torquing down a nut or a bolt unless you use a torque wrench, and now you have folks in production having to use torque wrenches. And that takes time and is expensive. And it's always better to figure out a way that will provide some consistent clamping force without having to use a torque wrench if you can get away with it. Also depends on the volume of your production, how much makes sense. Clamps or the pneumatic actuators that I showed in our earlier systems can provide nice options. I actually did a check once to see how much difference it can make to torque the bolts on a fixture to different settings. And here you can see the response on a product before and after a torque change. And what I did was fixtured the product for halt, got everything ready to go, and then just tightened every nut down another turn or two. And I saw a difference in the G level that I achieved for the same set point, dropping from, or going, I guess, up to 40 Gs after the tightening of it. Before the torque change, it was only 20 Gs. And you can see, well, it's kind of like tuning a guitar. The tighter you twist it, the higher the spikes, and they can move around. So it makes a big difference when you're trying to get consistency from test to test. In HALT, you are measuring these spectrums and recording them, so when it comes time to repeat that, you can take the time to look at spectrums and adjust torques as necessary to make them match. You get into a HASS environment, you don't have that time or that luxury. You need to know that these spectrums and G levels will be approximately equivalent without going to the trouble of measuring them. You need consistent clamping capabilities. And here's an example, a drawing of a fixture that we had designed for a customer. Here's the unit under test is being clamped here between these pieces that protect it, done similarly to that power supply fixture you saw earlier. And here's the pneumatic clamping device that pushes down on the top of the unit. And during fixture validation, you can make sure that all of these units are receiving the same excitation inside of the product. You know, I have kind of glossed over it, but I assume the understanding is that when you're looking at the vibration in the system to be sure that it is uniform, you're not concerned with what the set point is, and you're not concerned with what the table is doing. You're concerned with the response of each of those individual products. And I'll get into the discussion of fixture validation in just a few slides here. Now here's another example. Here we see those power supplies with the pneumatic clamps across the top. And here is the control box that is used to control the pressure to each one of those clamps. And actually, each one of these is setting the pressure to all 6 of the same position on the 6 tables that are in the Q-Fusion. The pressures were necessary to make each position in the fixture give the same response with that table input. The table input is the same on the 6 tables. So it wasn't necessary to have individual control for all units, only for each location in a fixture. Now we'll talk a little bit about fixture validation. Once you get a fixture designed, that's often the easy part. Then the surprises can come, because you need to be sure that your units are receiving equivalent stresses in all the locations of the fixture. Typically, we'll look for a consistency of vibration in the range of plus and minus 20% for a GRMS reading. As far as spectral content is concerned, that tends to be a little more objective, but take a look at it and make sure they're not dramatically different. Thermal consistency, and there I'm talking about the temperatures reached in dwells as well as the rate of change as during thermal transitions. We like to see about a plus and minus 10% across the population. In both these cases, I'm not talking about a percentage relation to set point. I'm talking about a percentage relation to the average value. Then you can adjust the set point so that that average value is the desired value for the product. But it should be what was measured on the product that is the average that is used for these comparisons. The easiest way to do that verification is to take one product and completely instrument it with all the necessary thermocouples and accelerometers, then move that instrumented product through all fixture locations, going to the desired vibration levels and getting the readings at each one of those locations. That is a lot easier and more consistent than trying to move the accelerometers and thermocouples from product to product. Slight variation in the location of those sensors, as I've mentioned, can make a big difference in the readings you get. So you eliminate that variability by simply moving one unit through all the positions. something to keep in mind is we like to have the rest of the fixture completely loaded. It will change the way the fixture responds, and so especially if you have a massive product. So keep the rest of the fixture loaded during that fixture validation. You'll get a good idea of how consistent things are. If things aren't consistent, you can make some changes in, obviously, we can talk about torque changes. Another thing to consider, if we find that consistently one spot in a fixture has some reduced vibration level, is slight dimensional changes in what's clamping the product at that location in the fixture, so that things even out a little bit more. That's all part of the fixture validation process, and that's all an important part of the entire HASS setup. Now, once we've completed getting a fixture done and finished our halt so that we have our levels, it's time to get the HASS screen levels themselves set up and do proof of screen. And we'll get into these in some detail now. As I mentioned, the profile in terms of the thermal and vibration limits that you use is based on that initial halt information. And you'll hear bandied about occasionally using the 80-50 rule of thumb. And it's based on what has historically worked well, and what has worked well is setting the thermal range that is used in HASS to 80% of the range that was found for limits in halt, and also setting your vibration levels to 50% of what was found in halt. These numbers reflect to some degree the fact that we don't have much thermal fatigue happening during a halt or during a HASS. Even though we're using high thermal levels and high thermal rates of change, it's just not much time, and there isn't time for a lot of fatigue to happen. So there's not a lot of life being taken out of the product due to those thermal fatigues. Vibrationally, however, we do fatigue the product. So we reduce that limit by half to ensure that the fatigue induced by the vibration is down to a safe level. This is where we start, and typically with an initial screen length of 2 to 4 hours, depending on how long your functional tests take, and looking at initially vibration duty cycles of 25 to 50%. There's a lot of judgment work that goes into the initial setting up, depending on what you found for your product, how robust it was, how sensitive it may be to cosmetic damage during vibration. In the end, the proof of screen will let you know that what you have settled on is effective and safe. So a little bit of variability here is tolerable. And once you have finished halting a product, you have a lot of room to work with. You've got very wide margins and a high tolerance for this type of fatigue when you have a product that's gone through halt and had corrective actions done. Now, you'll take a look at when and how you're going to be running your functional tests during the profile. Again, you had some nice luxuries in halt. If you needed a button pushed, you could do it with a rod through the porthole. Now, you need to consider different ways to handle problems like that, how you can completely automate the test, and when you're going to be running those functional tests. In general, you want to, if possible, treat it like you do a combined environment test during halt. At least do a complete functional test at the end of every thermal dwell. If possible, be functionally testing continuously, and include power cycles as part of the functional testing. It's a very important piece of it. Any product-specific stresses that you used in halt that look like they'd be good to include in HASS, decide where to put those within the profile. Things like thermal loading and the power cycling I described is often considered as a product-specific stress. You can load those in and improve the effectiveness of your screen. In general, I'm sure most of you have seen this slide before. When you have finished doing your halt, you have found operating limits, upper and lower operating and destruct limits, and you've got operating margins and destruct margins. In this case, the stress must be thermal because we have upper and lower limits. I put this up here to give you an idea of what we're talking about when we use our 80-50 rule and set up our new limits for HASS. Because now we're wanting to stress the product not to a point where we're actually going to damage it by getting into the distributions, for example, on this destruct limit, but to a point where we would expect it to not be damaged. We're outside of the limit here, but typically far outside of spec. Now you'll note here I'm introducing the idea of the two-part HASS screen, where you have a precipitation screen followed by a detection screen. And the precipitation screen will stress the product to levels beyond the operating limit. So you don't expect the product to be operating here. We've pushed out beyond the operating limit, but if you recall, the operating limit is characterized by soft failures, not hard failures. So we don't expect to be damaging the product. We are well within the limits of this destruct limit. So at this point, we would expect the products are not being damaged. They may not be functional, and it's a engineering decision of whether or not they're powered at that point. But the important thing is we're outside of the distribution for this destruct limit, so we shouldn't be breaking product. If something has happened, some weakness has crept in or some cold solder joint has popped up and it has caused this destruct limit to come in, then testing to this point will catch that. And that's the whole purpose of going outside of these limits as close as we safely can to the limits that we found in HALT. So if anything moves here, and there's, due to whatever change, you will detect it here, or rather precipitate it here in this precipitation screen, then you will follow that with a detection screen. Now your unit's powered on and functional. You would expect it to work because you are within your operating limits. So the unit's functional now, still outside of your specification, which is something you really don't care about, what the product specification is when you do these tests. The tests are based on what you found in HALT. And you expect to be functional because you are within the distribution on this operating limit here. The detection screen will see if anything broke here, if we failed anything in this part of the test, and also it will find out if anything has shifted in this operating limit. Some new stack up has occurred in the response of the product to temperature, and now for some reason the product isn't operating at this point like it used to. Now this whole setup represents what is sort of an ideal screen, or a can't even quite say typical, almost idealized screen. What often happens once you have finished ruggedizing your product is that this difference between operating limit and destruct limit becomes quite small. And the feasibility of doing separate precipitation and detection screens goes way down. There's just no place to put a precipitation screen because things are too close together here. If that happens, then you're doing a single screen, a detection screen, where you're powered up, functional, and pushing out as far as you safely can here. If you're doing a two-stage screen, this limit is based on the destruct limit you found in HALT. If you're doing the single-stage screen, then this limit is based on the operational limits that you found in HALT. Now, if you take all of that and you turn it into an actual screen and look at the levels, you'll see things like this, where I have vibration on continuously, and I have thermal extremes that are beyond what I found in my operating limits, but within these destruct limits, which is what these lines are. And we'll see power cycling going on now. At this point, we'll turn the unit on. We're within our operating limits, and we're running our diagnostics during this detection portion of the screen. Now, once you have come up with the screen, you must do a proof of screen. One of the things to consider back here when I'm talking about these distributions and staying within these distributions is I have no idea what those distributions look like. I've tested 4 units maybe in HASS or in my halt, and I really don't know where they are. The 80-50 rule of thumb gives me a place to put lines, but I really need to be sure that I'm not going to be damaging good product, that I'm not getting into that distribution. And I want to be sure that I'm finding failure modes, that it is going to be an effective screen. And we do that empirically by using proof of screen to serve those 2 key purposes. First, consider proving HASS effectiveness. That one actually can be the trickiest part. I want to demonstrate that my HASS will find bad boards. In order to do that, I need bad boards, units that I would expect to fail in HASS, but that do not fail under my normal testing that I do in production. If you have boards that have been out for beta, or if you're introducing HASS into a unit that's been in the field and you have some returns to work with, and some of those returns have turned out to be no trouble found units where it seems to work fine now, those are great for testing HASS effectiveness. You can put those in and see if the HASS screen will drive out a failure in them. Then if the HASS screen that you proposed doesn't show you failures in those, you may have a perfectly functional board. It might make sense then to go on and put that into halt and see if you can break it in halt and at what levels. That will give you a very high confidence that you're finding bad boards with your HASS screen, and if they get through the HASS screen, then they're good boards. As we all know, that happens, that those get returned as well. So when you're testing that HASS effectiveness with the no trouble found boards, get everything cabled in and functionally tested exactly like you will be doing in your normal HASS. You should see those boards failing within the HASS profile. If you've got an ability or a way that you're sure will seed a defect, then by all means seed defects in these systems. The problem is it can be difficult to seed a defect that will pass functional testing in your production line testing, but then be expected to fail in HASS. If you have a way to do that, do it. If you don't have a way to do that, work with NTF boards and see what you can find out from those. If you are totally incapable of doing any of that and you really can't figure out a way to get your hands on boards that you expect to see fail, you'll find yourself in the same boat that other people are occasionally in. And then what you wind up doing is tuning the screen in production. And I'll talk a little bit more about that as I move on. But this is the step that is the performance portion of proof of screen. We're demonstrating that we will find the flaws we need to find. The other thing that concerns people is I am putting a lot of stress on my product here. I need to make sure that I'm not taking excessive life out of the product. And that's something that worries a lot of people, especially when they're not familiar with halt and HASS and they see a machine that's shaking a product that is never going to be subjected to vibration in real life. Isn't there a chance I might be hurting my product here? Proof of screen, the live portion of proof of screen is what puts that to rest. Basically now you're working with new boards that have passed all tests and are believed functional. And you will use typically a chamber full, if a chamber full turns out to be 10 or more. If not, I'd like to see this test done on 10 or 20 units. If you're in high production or high volume production, you ought to up that to 40, just so you've got enough units to have a really good feeling about the live portion of proof of screen. Now you're going to be taking those boards and subjecting them to 20 to 50 times through your HASS profile that you've determined is effective and is the one you want to use. For example, if your HASS turns out to be 3 thermal cycles long, one HASS screen is 3 thermal cycles, then you'll be running 60 to 150 thermal cycles on this sample of 10 to 40 boards. All boards should be able to live through that. Going through this many cycles of the profile, which really is a lot of abuse, might be something that you would think a typical board isn't capable of, and perhaps the typical board wouldn't be. But if you have done HALT and done it well and implemented your corrective actions, there's no reason to think that a board shouldn't be able to tolerate 20 to 50 times through a HASS screen that is uses our rules of thumb as a starting point and has been shown to be effective. So watch those boards, watch them all pass. If they do, you're happy. If something fails, find out what happened. It's always possible that out of those 40 boards, we had one that was bad, and we caught a good one there, in which case, good for you. But take a good look at them and make sure. Really what we're doing is seeing if 20 times through the cycle has not reached the end of life of the product. We haven't fatigued it and beaten it up to the point that it dies at the end of, say, 20 cycles. Then one time through the screen will remove less than 1/20th of the life out of the product. If you make the assumption that one more cycle would have broken it, then I will say that one time through it will take 1/20th of the life out. And that means that if I run it through twice, because maybe I found a problem, I reworked it, I want to send it through again, so the board wound up going to HASS twice, I know that I have removed less than 10% of the life of the board. If my proof of screen was 20 cycles, my proof of screen was 50 cycles, then I have a much higher confidence level that I'm taking extremely low amounts of life out of the product. The question of, am I really only taking 1/10 of the life out of the product by sending it through this screen twice? This is a lot of, these stresses are very different from what it sees in real life. Does this still work? And I actually wrote a paper on that topic, and it's going to be available in the next week on our website concerning the fraction of life removed by doing HASS, and does proof of screen actually prove that? I can save your time if you don't want to muck through all the math in it and say, yes, proof of screen works, and we can fall back to the basics of how fatigue is analyzed and say that you're safe if you do proof of screen. And the kind of failures that you find in HASS are typical of the failures that you will see popping up in the field: mechanical tolerance issues, IC process problems, timing problems, the things you identified in HALT, as well as production issues. These are all the classical failure stuff. One of the key things with the HASS is that you respond to these as soon as you see them. Don't be fooled by the fact that you only saw it on one unit. You're seeing the tail of a distribution, quite possibly. You want to jump on those failure modes when you see them. Now, an interesting characteristic of HASS is that it might make sense to make changes in that screen based on the kind of results you're getting, or if you make changes to the product. Initially, when you're setting up a HASS screen, I like to set it, if possible, get it set up so you have 4 or 5 thermal cycles. This gives you some granularity so that if you have to, as I mentioned earlier, tune the screen in production because you can't really tell how bad boards are responding to the screen, if you have 5 thermal cycles, you can look and see, where are my failures happening? Are they happening in the first cycle, third cycle, fifth cycle? As the product matures and production matures, you will see where your failures are happening. If everything's happening in the first 2 cycles, you're happy, and you reduce your screen to 3 cycles maybe. Or after you've been building this product for 6 months, you may see that gradually shift down to just a single cycle. Everything that's bad is getting caught in that first cycle. Everything else we've learned how to do right. In that case, let's drop down to 2 cycles in production. You can shift that around as you see fit to reduce costs and increase throughput. Now, if you run into the situation where those failures are evenly distributed across your 4 or 5 thermal cycles, now you'll say to yourself, boy, I wonder what happens in the 6th cycle if I was running 6. I hope I'm not missing anything. And let's do make very sure I understand the failure modes that I'm seeing that are coming out of here. And maybe I need to increase my number of cycles or increase vibration levels to make these failures happen sooner. Now, another interesting point is that it may make sense to change your screen when you get changes to your product. If you were doing a burn-in and someone introduced a new component and said, now we're going to have to make burn-in shorter because the new component can't stand it, then that's sort of a ridiculous thing to consider. But if I have a new power supply, for example, that's got a lower thermal cutout limit on it than my earlier one had, then it might quite be possible that it makes sense to reduce my thermal stresses and actually so that this new part can be used and with no reduction in the effectiveness of my screen. You'd have to do some evaluation there, but it can make sense. And careful thought and justification is required to do that. Now, I did want to mention a few things about our QFusion product. Here you see a picture of it in use. We've got, as you saw earlier in the earlier pictures, 6 tables. It has split doors. This product has been designed specifically for HASS and high volume use. And you can get tests done with a much lower cost per unit tested and with much less floor space per unit tested than you can with any other unit. And I also wanted to be sure that you knew that the Qualmark HASS and HASSA guidelines are available online. We've written a document that you can use as a boilerplate for your own descriptions in-house of how we do HASS, as well as HASSA, a highly accelerated stress audit. That's something that we haven't gone into a detailed description here, mainly because the setting up of the screen for HASSA is identical. But in HASSA, we're not doing 100% of the product. It's just a sampling. And the sample level, the process for determining that, and considerations around that are described in our guidelines. So those guidelines are available for your review, and there's also technical papers on our website that give you some insights, some case studies with some practical experiences on using HASS. And one last comment about Qualmark Center of Excellence. Tom Peters, myself, and the R&D group that we have here and several other individuals are involved in our Center of Excellence. We have many years of experience actually doing HALT and HASS and HASSA, and we have subject matter experts throughout our industry, throughout our company, that we can bring to bear on your problems. So we can quickly come up with fixturing solutions and quickly come up with the right screen and doing proof of screen so that you can realize the benefits of HASS or HASSA very quickly. These are services that we offer and we'll be happy to discuss with you. You can email the COE group at excellence@qualmark.com. And with that, I'll turn things back over to you, Gail.
Okay, great. Interestingly enough, we've just had someone go over to the HASS guidelines page. The page was not found. We were just testing that yesterday. We will go look at see what the glitch may be and get whatever error has occurred corrected, so you can put your hands on those HASS guidelines as soon as we get off the phone here. So, Neil, we do have some questions.
Okay.
One, are you with me?
Yes.
Okay. One of them is, okay, you've got Q-Fusion, but I'm doing halt in a Typhoon chamber. How do I go about getting the numbers needed for HASS and a Q-Fusion?
Oh, yeah, that falls back some to the discussion I was having about the differences between a halt fixture and a HASS fixture. In general, as long as you are very carefully taking data on the product itself, so you understand the stresses that are seen, especially at key areas in your product. If you know of particularly vibration-sensitive areas, of course on the surface of any circuit cards, etc., you know how they're responding in halt, and you know at what levels they failed in halt. That's the number you look at for correlation when you move into a Q-Fusion. Your product may be oriented differently. It's certainly going to be held down differently. The relationship between table input and product response has undoubtedly changed dramatically. You don't really care. You know what you need to see for a response, and you adjust input until your response matches. So instrument your product well in that halt and make sure you have the data you need to establish a correlation when you get into Q-Fusion.
Okay, great. Also, the question is back on slide 21.
Mm-hmm.
Do you recommend loading the fixture in the middle of the table, or is there preference for loading on the table in a particular quadrant?
Yeah, I touched on that, but I may have said it too quickly. You see this fixture located in the center of a quadrant. It's not in the middle of the table. If you can kind of imagine the edge of the table would be out here somewhere. And we're actually centered in the quadrant that's closest to us in this wall. On the table, when you're dealing with fixturing on these on the large tables as opposed to Q-Fusion, you have basic symmetry around the center of the table. The table flexes and moves during vibration and has all its own modes. And the centers of the quadrants tend to be very similar. The vibration is symmetric in the quadrants. So I will always fixture in the center of a quadrant even if I am only testing one unit, simply because it's not at all uncommon to be testing a unit again later or to be testing 2 or 3 units later. And if that happens, I want to be able to have the same vibration, basically the same correlation between fixture and input that I had when I did that first halt. So I always center in quadrants just so if I need uniformity later with multiple units in, I will have it. And if I don't, it doesn't make any difference. Centering in the middle of the quadrant works just as well as anywhere else. I kind of avoid the center because if I put something rigid in the center of the table, if it happens to be a big rigid product, it will dampen the center of the table and make it more difficult to reach higher G levels because it dampens out one of the key modes of the table.
Okay, and another question. When there are failures before the 20 cycles, is there a suggested way to reduce the stresses if the failures are caused by wear out due to excessive stresses?
If you're seeing wear out failures, there are undoubtedly vibration wear out failures, and the easiest thing to adjust is either the level or the duration of the vibration. If you reduce the level of the vibration, you're reducing something that has an exponential relationship with fatigue. So a drop from, say, 20 to 15 Gs in the response of the product will be a significant drop in fatigue. If, however, you leave it at that same level but cut the time in half, you have simply reduced the fatigue by half because the fatigue accumulates linearly with time. So either level or duration. If you cut duration, then you may wind up enjoying the advantage of reducing the total time of the screen, and that's always nice. So you might start there, and it also gives you a little more control over the amount of fatigue reduction because we know that it's linearly related to time of vibration. So that's the first thing I'd start doing, is cutting down the duty cycle of the vibration.
And this is Tom Peter. Just like to elaborate a little bit on what Neil just said. And that is, when you do have failures, it is very critical to do root cause analysis before you start adjusting your screen, so you understand the failure mode. Because typically, HALT has proven your item shouldn't be wearing out at these levels. So if you're getting things to wear out, you need to make sure that you have data on hand that would indicate either a screen adjustment or you had a faulty product. Then you need to figure out why that is. So just a little bit of elaboration on that.
Thanks, Tom.
Okay, and I think we've touched on this, but if the proof of screen fails, does it indicate that the screen is too strong? Conversely, if proof of screen passes, does it mean the screen is not effective enough in precipitating failures?
I understand, I believe, the nature of the question. If I do my 50 cycles and never see a failure, what confidence level, does that mean something? And if I go 30 times through and do see a failure, does that mean something? And if I do 2 passes and see a failure, what does that mean? And the whole interpretation of that becomes, the failure analysis is critical because you have to learn why these things have failed. If the failure that happened a few times through the screen was one you're glad you caught, then you're glad you caught it. If you run a screen 30 times and you get a failure and you do failure analysis and you say, this is clearly solder fatigue, and when I look at the solder joint, it looks to me like it was done just fine, and the other solder joints that are near this one on the board are showing some cracks and signs of fatigue as well. So it looks like we're starting to wear this board out. Well, that seems, at 30 times through the screen, is that tolerable? Then it becomes an engineering judgment call, because how many units did I test? And if I'm only going to go through the screen once when I'm in production, then that's 1/30th of the life of the product. I can tolerate that, and I've got a really good feeling that I'm going to find everything because I'm pushing it pretty hard, evidently, because I saw that failure at 30 times through. If I go through 50 times with no failures, then I'm happy with that. I want to be sure my screen is effective, that I am finding bad units, so I'm looking at that the screen effectiveness part particularly closely and making sure that I see something there. If I'm not able to do the effectiveness, and I'm going to watch very closely as I begin production to see when units fail in my screen. So yeah, it's quite possible to go that 50 times, not see any failures, and come to a valid conclusion that, good, my screen's safe, and look, I've shown my screen is effective, that's all I need. I've heard stories of people doing hundreds of passes through screens with no failures when they have good units. But if they've got a unit with a defect, it falls out real early. In all cases, failure analysis is critical of all failures that are found. So you know if you're looking at fatigue stuff, if I'm looking at something I should have caught in HALT, or if I'm looking at a new failure mechanism.
Okay, Rahul, I'll respond to your question offline. One note about the link to the HASS guidelines. When you submit the request form, you do not immediately receive the guidelines. Rather, check your email, because we email the link to the guidelines to you. So maybe that will clarify the way that particular process works. Also, with the questions about the proof of screen, I'm going to plug Qualmark COE for you guys. They've been doing this for 20 years plus. They've seen just about everything that can crop up. So they are available. Drop them an email at excellence@qualmark.com. If you engage the COE, a lot of times you can get to solutions a lot more quicker than trying to determine things on your own. I do appreciate all these good questions, and I'm sorry that we have run out of time. If you want to submit more questions, please enter them on the survey form that will pop up at the end of the session today. So I'd like to thank everyone for attending. You will receive a follow-up email with a link to the recording of today's webinar should you want to revisit any portion. Several of you questioned, and yes, the link to all of the recordings in this series are available off of our home page. If you go over to the right-hand side, you'll see all of them listed, and each one of them has their own link. When we conclude the session, this whole series, the plan is to bundle it and make them all available off of one landing page. I'd like to thank the Qualmark COE team for hosting this special Ask the Expert series and for sharing their knowledge about HALT and HASS can be so effective at helping companies reduce their warranty costs. Qualmark Center of Excellence was established as a central source repository for our customer and partners, where our 20 years of knowledge can be focused on delivering effective product reliability solutions. I invite you to send an email to the team at excellence@qualmark.com to start a dialogue about how Qualmark can help you reduce your warranty costs and improve product reliability. Also, you guys will want to visit our online library at qualmark.com. You'll find lots of helpful documentation about HALT and HASS testing, as well as information about Qualmark products such as QFusion, as well as COE services. As you log off today, I encourage you to participate in our survey. Your responses help us develop future Ask the Experts discussions. I know all of you like to learn about what is working in other companies and in other industries. If you have an interesting case study you'd like to present, please touch base with me and let me know. Send me an email to events@qualmark.com. Thanks again, everyone, for attending. We'll see you next month for effective fixturing. This concludes today's session.